So good morning. Continuing from what we had done beforehand, in discussing the laws of motion, we discussed the second law of motion, which states that the force is directly proportional to the time rate of change of momentum, where momentum is mass into velocity with a unit of kilogram meter per second. And so, like we have done before, when there is y is proportional to x, then y is equal to kx. So, where k is the constant of the proportionality of the system, and we found that we can write it as f is equal to k dp dt, which we can write as k dt dt of mv, which, because there are two functions, the first function is m, the second is v, so we write it with the rules of doing differentiation, the first function differential of the second function into differential of the first function multiplied by the second function. We discussed the beauty of why we take this kind of a thing and not like this, that the first function differential with the second function into the second function the differential with the first function. We don't do that because the multiplication of the two functions, we don't know whether it is a simple multiplication or it is a cross product of the two of them, which we'll discuss later on and show that if it is done with what my brothers and sisters in teaching you mathematics, they avoid it, but we are not going to avoid. We find that for the velocities that we are dealing in, the dm dt is equal to 0, and I told you that the mass changes with the velocity, particularly when this special theory of relativity says that the mass enhances as the velocity is increased. But here the case is that the mass is taken as almost constant. Then we find that f is equal to km dv dt or kma, and we choose the value of k equal to 1 by choosing the proper units. The unit of force is described as 1 Newton, mass is kilogram, and acceleration is like this. And I said that if there is no force acting on the body under consideration, whether the body is at rest or the body is in continuous uniform motion, in both the cases, if the force is missing, then we have a manifest of the first law, and I said that the first law is hidden inside the discussions of the second law. Before, I told you also the basis of how to look into the third law, but before that I would like to do a very simple exercise for us, and that is by taking the force as the force. If I describe by force, F is equal to ma. F is equal to the mass multiplied by the acceleration of the body. F is equal to ma, which is the description of the second law. Also I can write it as m is equal to dp dt. So suppose my force is in the three-dimensional space continuum, and of course we have the x, y, z and axes to describe the motion of the body, and in the space-time continuum we have another variable which is time. So I can write my f as equal to fx. I can resolve it in three parts: fy plus fz and this I have to do because one of the followers of the lectures has emphasized as to how the resolution takes place. So just to cater to that, I can write this as equal to fx, which is the magnitude, and the direction vector in the x direction I cap plus, this we have done earlier also, y j cap plus fz k cap. And I explained in this system of the coordinate system that we use, x, y and z, which is perpendicular to the plane like this, so they make angles of 90 degrees each. I emphasize time and again as to what is the concept of the 90 degrees. The cos of 90 degrees is equal to 0. So these parts we have here, and so I can write also the acceleration as equal to ax I cap, I skip one step, ay j cap plus az k cap, which are the respective accelerations magnitudes along the x direction, along the y direction, along the z direction. It's written like this. Okay, so I can write from this relation that the value of f square is equal to fx square plus fy square plus fz square, and which gives the value of f as equal to under root of this same thing, under root of all these of fx square plus fy square plus fz square, which I am not writing for you, and similarly a square is equal to ax square plus ay square plus az square, and therefore a is equal to the root over of all these quantities, the sum of x square plus ay square plus az square, etc., etc. So this is how we can understand by resolved parts along the x-axis, where the unit vector is I cap, here I have the j cap, and here I have the k cap, and of course multiplied by the resolved parts of the force and the acceleration. And of course, if the force direction is like this, for example, if the force direction is like this is the force, then one thing which is imperative is that the acceleration should also be in the same direction. Okay, so this we have to understand. like ax I cap and fx I cap, they are in this direction, fy in this direction, and fz in this direction, along with ay and az. So this is how we can apply it for the three dimensions that we are aware of in the space-time continuum. And now I pick up what I did for the third law before going to the concept of momentum and the discussion about how the momentum is conserved for a set of bodies. So suppose, imagine a universe where you see that the body of mass m in a frame of reference is at rest. And another body again of the same mass m, here we say that the velocity, associated velocity, is equal to 0. This is the position of rest, and the position of uniform motion is such that the uniform motion, I'm just writing like this, without a change in the direction and without a change in the speed of the object. In the case of the uniform motion, the velocity is not equal to 0, the velocity is rather a constant, is equal to a constant, does not vary. So now, in the vast set of problems of motion that are encountered, Newton thought that I cannot do with these two laws, the first law of inertia, the second law, where F is equal to ma, and he thought that in the first instance, if you look at these two bodies and you look at nothing else, you can see the space where this body is located or where this body is moving. So you don't know that you think rather that there is only one body in the universe. No other body is required. But if we want to make a change in the state, in the status of the body of uniform motion or the position of rest, then a force is required. Because in these cases we say that the net force acting on this is equal to 0, and the net force here also acting is equal to 0. But if a change is taking place, then what Newton said, that at least one more body is required. One more body is required, and that which imposes, which creates, which which is the cause of the external force which is acting in a body. So he thought that there should be at least, at minimum, there should be two bodies. Let's call these bodies as number 1, and located a distance away from it, there is a body 2. The motion, if you hold the two of the bodies, and if there is a force which is in the line joining the two bodies, and if we call this force as F12, I call this F12, I am conversant with F12, and I read it as follows: force on body 1 due to body 2. Some authors, they say that force by body 2, they write here 2 and 1. But I will take and I will suggest to my students here, those who are with me, to understand F12 as the force on body 1 due to body 2. Okay? Similarly, R12 means from 1 to 2. The vector from 1 to 2, etc. And what he suggested was that the two appear to be in the same direction, on the same line. There is a force F21. There is a force F21. Okay? Of course, it is also a vector, and you can see the direction of this vector is opposite to the direction of the force vector. Okay? So, there are two bodies. Now the interesting thing is, that both the bodies are interacting with each other. Suppose we were holding the body 1 and 2, and suddenly in this situation that is there, we relax these two bodies, then what happens? That the two bodies start moving towards each other. Okay, and after some time maybe there is a collision. So we'll come to that collision part later on, but right now I'm saying that this has the tendency to move towards the body number 2, and this body has the tendency to move towards the body number 1. So these two forces, which of course are governed by Newton's second law, these two forces have to be there, and there is some kind of an action which is there. I will not call this as action and reaction, but I'll call this as an action. This activity is an action at a given time, and this activity is also an action. Okay. And if there are two observers, me and you, there are two observers, and I say, I look at this body and say that there is an action on this body by the second body, and I say, look here, look at my finger, I look at this pen. I'm saying that to every action there is an equal and opposite reaction. And from among you there is somebody who looks first here and then says like this, that to every action there is an equal and opposite reaction. Action and reaction is a pair of forces which take place simultaneously. There is no time lag or lead between the two actions. So, my observation that to every action there is an equal and opposite reaction, and your observation that to every action there is an equal and opposite reaction in the same frame of reference. Who is telling the lie? Am I telling the lie? The answer is no. Who is telling the lie? You are telling the lie? The answer is no. So if both of us are not telling a lie, then that means both of us are going with the truth of whatever is happening over here. And we have to describe these two things. So we said, I told you that in 1980s, when the people were very conscious about these laws were revisited and this and that, and then they said that this is interaction. And to take you away from the, what is the general language says reaction follows action. Instead what they said that well let us agree to rather introduce the following utterance or statement about the Newton's third law, and we will say that to every interaction there is an equal and opposite interaction, or at the same time we can say to every interaction there is an equal and opposite interaction. So what happens? What happens is very simple, and we can write that this is the statement of the third law. Is equal to minus F21. The force on body 1 due to body 2 is equal in magnitude, yani F12 this I can write it as F12, the magnitude, and F21, the magnitude of this also can be said to be equal to F21. So magnitude wise the two forces are equal, and we can say that from this relation, by simple algebra, I can say F12 plus the vector F12 plus vector F21 is equal to 0. Okay. So for the system of these couple of bodies, I have the net force acting on the whole system F12 plus F21 is equal to 0. And it is understood that there is no third body or fourth body or whatever. Okay. So all the bodies in the universe for the body number 1 are described in terms of body number 2. There can be masses. The masses you can write as M1, and mass here is M2. M2 may be equal to M1, M2 may be equal to M1, may be greater than M1, and may be smaller than M1. Okay. In all situations, the F12 will be equal to F21. In a simple situation, like we have in the case of a body falling on the surface of the earth. This is, we show the surface of the earth with its curvature, and there is a body of mass m which is at rest at a certain moment, and then this starts falling towards the earth, which has got a mass m and which has the radius r, and the distance between the two bodies is equal to, you can say, r plus h at a given instant, where h is a function of time, but h is being so small as compared to r that when this body is falling towards it, I can say this is approximately equal to r. It will not change, and because the value of h, even if it may be a kilometer or so, is very small as compared to r, which is 6,400 kilometers. Okay, so what is going to happen? How we describe this law? We say that this is F on body m due to body capital M. Try to understand that. This is the force. Force on the mass small m, which is, of course, small m is also very small as compared to capital M. Is very small as compared to capital M. Okay. So this body is falling towards the earth, and the force applied on it is Fmm. So the question is, where is the other body located? Then we have a center of mass concept and etc., and we'll say that let this body here may be at the center of the earth. There is a center of the earth here, and I can say that the mass is capital M. Okay. And the mass is capital M. So what does this law say? That there are two bodies, one falling towards the earth, and then it is far away, but I am showing it here, and I will say that in that case there will be the pair force that will apply at the center of the earth. And this pair force I can write as F on body M due to the body of mass small m. The two forces are in the line joining the center of the earth and the position of the mass. So all the time, now somebody asks, what do you mean? This tiny pithy body, this is also having the same force on this massy earth? Yes, my dear, that is true. The two forces have to be equal to each other. So another one from you is going to ask me that this body during the fall is gaining velocity. Because of the acceleration due to gravity, this body is continually changing its velocity and falling on the earth. So how do you explain that? I'll say, yes, my dear. When this body is falling here, whatever its velocity, it will have a momentum associated with it, which is small m into small v. Then this earth will also fall towards the body. Will fall towards the body, and you will see in the due course about the law of conservation of momentum that for the earth body system, the total momentum of the system remains conserved. But here it is the occasion to talk about these things. Now, I said that in Principia Mathematica, if you open the book where Newton had a copy himself, not this book, this is by NCERT. Okay, so there used to be a side where anybody could make annotations. Some of the students, they don't want the page to be destroyed when they scribble on the side of the right footnotes. My suggestion is that if Newton has to write on the sides as to what is there, then why not me? Why not you? Okay? Everybody should feel proud of adding his or her notes in the book. Underline the things with highlighters or pencils or whatever. And what did Newton write? Newton discussed he had a problem in solving the questions related with mechanics of earthly bodies and also of the celestial bodies. Then the problem that he was facing, Newton came with an idea. And the idea was, what is the state of motion of body? And what is responsible for that state of motion of body? For example, I told you, I'll just introduce to you like this, that there is a body which is lying on the top of your table. And when you look at that, you say that this mass here is at rest. And I told you before, I reiterate, I write again, that there are at least two forces as we understand. One is the force mass into the gravitational field in downward direction, and another is the reaction force of the surface on which the mass is lying. And the two forces are equal and opposite to each other. Okay, and therefore we say that this is in the state of rest. So what Newton wrote on the side of his copy of Principia Mathematica, which was published and was not published before Newton, republished before Newton died. Newton did not have an occasion to that, and then his lab and everything, but at least the room in which he used to work was sealed, was under high security. So what are the annotations, what are the writings, what are the loose papers, etc. They are all there in what is called the Archives of Newton, but this is not open to public. Okay, because you know they are very precious things, and we are afraid of somebody stealing that. So the American professor I was talking about, he is committed theft. He stole into that room, and there he spent continuous hours to learn more than what he used to know. And there he came out with what I am going to tell you about the concept of Newton, that was state of a body. So in the state of a body, what Newton says, Newton says that the state of a body is determined, is described therefore by the forces acting on the body, and not by the forces that the body exerts on other bodies. I'll use that concept with you to learn, solve some of the problems, interesting problems that have been reported, that are there, and in understanding them we have some kind of a trouble which can be done away with by Newton's simple advice that the state of a body, I'm not writing here, the state of a body is determined. You can write in your books, listen it carefully. Again, I say slowly, the state of a body is determined by the forces acting on the body, and not by the forces the body exerts on other bodies. So the system is not a simple two-body system. We can have, even in the presence of many other things, many other bodies, many particle systems is still there. This is applicable. So for each pair of them, like I said, in the case of gravitation I took this. In the case of gravitation, explaining to you about two masses m1 and m2 anywhere separated by distance r, and we found that the magnitude of the force is given by F is equal to capital G m mass product of two masses upon the distance between the two, of the separation between this, where G is the universal gravitational constant. It has been the same value in our system of units as we defined millennia ago, and will be the same millennia hereafter. It is independent of the structure of the universe, etc., etc. This is what I told you about the gravitational system. And in the system of two charges separated by distance r, charges q and capital Q, I have 1 upon a constant 4 pi epsilon naught, as I introduced to you when I said that Coulomb's law can be described here, capital Q upon R square. So this is the same way, 1 upon 4 pi epsilon naught, where epsilon naught is permittivity of free space, the product of the two charges, 1 R square. Well, I have grouped these two. I have grouped these two because why? Now I am just telling you, and you know it. Whatever you know, I am going to tell you that we have two particles. These two particles, I have a particle, I show it like this, put in space, away from another particle. The distance between the two particles is r. There is an inverse square law in both the cases. This particle has got a mass. This particle has a mass, let us take it, capital M, which may be smaller than small m, whatever value, it doesn't matter. But the same particle has a charge Q, and this one also has a charge Q. I use the term particle, but now I can say the body has got a mass M and the body has got a charge Q. This mass, that mass is always taken as greater than 0. Of course, there is the concept of negative mass in physics, which you may encounter later on under certain conditions. We have a negative mass, a concept of negative mass in doing the mechanics that we do there, in the semiconductor systems, particularly in the case of tunnel diode, Arisaki diode. So there we have a concept of negative mass. But the charge can have three kinds of values. Charge on any body can be greater than 0. And Benjamin Franklin, the American, said that the charge could be positive. Charge is equal to 0. That I will explain later on. A charge can be smaller than 0. According to Benjamin Franklin, this was negative. So we subscribe to what Benjamin Franklin, he classified electricity by the nature of the charge. The charge is positive, the charge could be negative. For example, the charge on a proton is positive, the charge on an electron is negative. The charge on a negative ion is negative, the charge on a positive ion is positive. But the charge on a neutron is equal to 0. So, in case both the charges are 0, then the force between those two 0 charges appears to be equal to 0. But if the two charges are positive or the two charges are negative, positive, positive, negative, negative, then this happens to be a positive quantity. Okay? And when a positive value is obtained for the force, that means the force is repulsive. The repulsive force. And if one of them is negative, the other is positive, then this quantity becomes equal to negative, and in that case we say the situation is attractive. And what happens exactly in the case of this gravitational force? there is attraction between two masses, okay. Similarly, there is attraction between two charges and the charges move towards each other. Well, so this is a small discussion about the third law of motion. In the third law of motion, which I have tried to explain out to you, F12 is equal to minus F21, and if either of them is said to be, these two is equal to, because in magnitude I can just say that F, and this is this F we are talking about here, also here. The force of between F12 or F21, the two forces, and then we say that this kind of relationship exists. So in Newton's third law, the state of a body is determined by the forces acting on the body and not by the forces which the body exerts on other bodies, which will show the difference, and that the two forces, these are called the bearer forces. One is, you can call action, the other you call reaction. The two forces are on separate bodies. It's not that like the case I discussed here, where I had a piece of mass where there was a reaction of the table and there was an action of the earth. These pair of two forces, okay, the reaction force which was in the upward direction and mg which was in the downward direction, okay, the two forces were acting on the same body. So the net force acting on this body, as we see in the condition of rest, that we also see is equal to 0. Okay, so I have tried to honestly deliver the various things about the third law, and it cannot be completed without taking some numerical examples, which we will take in the due course of time. But next item that we have to discuss is the momentum and the law of conservation of momentum before we go to impulse, etc., and solve some problems. So I hope, like I have enjoyed, you may also have enjoyed in tits and bits. So thank you very much for being with me, and do ask questions. There is a slot where you can go. Please just don't appreciate that, oh, amazing lecture, this, that. No, ask your questions, ask your doubts, so that if I am giving you an opportunity through the lectures to you to learn, I must also get an opportunity when you ask me questions, probing questions. Thank you very much. We see you shortly.